In this video, you will understand what is regression analysis, how does linear regression work, and how it is implemented, but in a very simple way. Regression is used to model or identify the relationship between two or more variables. By modeling, we mean finding a mathematical or statistical function that describes this relationship. This function could be like, where y is dependent variable, and x is independent variable. When we use regression for modeling, we can perform two main tasks. We can see how much one variable influences another variable, and we can predict the value of one variable using another variable. But what would be the statistical function for regression? It depends on the form of regression analysis to use. There are many forms of regression: linear regression, nonlinear regression, logistics regression, polynomial regression, and many more, each designed for specific cases. The choice of regression analysis depends on the nature of the data and the type of relationship between the variables. In this video, we will understand regression analysis using linear regression model. Linear regression model has two forms: simple linear regression and multiple linear regression. Simple linear regression is used to model or identify the relationship between two variables, x and y. X could be, suppose, outside temperature, and y could be electricity consumption, where x is the independent variable and y is the dependent variable. We can use simple linear regression to identify the influence of an increase in outside temperature on electricity consumption. Multiple linear regression is used to identify the relationship between two or more independent variables and one dependent variable. For example, we can analyze how does the increase in outside temperature and vacation influences ice cream sales. Here, the dependent variable is ice cream sales, and outside temperature and vacation are independent variables. In this video, we will understand linear regression using simple linear regression, as this is the simplest form of linear regression. You can then easily understand multiple linear regression by generalizing the concept of simple linear regression to multiple linear regression. In linear regression, independent variable can be of ordinal, nominal, or metric type. But dependent variable should be metric or continuous. Simple linear regression is used when there is a linear relationship between the two variables. Linear relationship means that the relationship between the variables follows a straight line when plotted in 2D space. Here, one variable changes at a constant rate with the change in another variable. When we plot data points of two variables on a 2D space using scatter plot, and observe that points follow a straight line path, then we say that there is linear relationship between the two variables. Thus, if variables follow a linear relationship, we can use linear regression to measure the influence of one variable on another. By this statement, I mean to say that it quantifies the change in y when change is made in one unix of x, and to predict one variable using the other. Linear regression analysis follows a well-known straight line equation, that is, y equals mx plus c. In the above straight line equation, m is the slope of the line, which determines how steep the line is. C is the intercept, which is the point where the straight line crosses the y-axis. Slope determines how much the value of y changes with 1 unit increase in x. The intercept is the value of y when x equals 0. When you draw a line through the data points and extend this line touching the y-axis, the point where it touches the y-axis is called the intercept. By adapting straight line equation to linear regression analysis, we try to determine the best fit line that determines the relationship between x and y. But what is the best fit line? When we plot all the data points on a scattered data plot, drawing a straight line using these data points requires the constant m, which tell the slope of the line, and the constant c, which tells the intercept of the line. So, you can't just guess and draw any straight line through the data points. You must calculate the value of constant m and c to draw the straight line that fits your data well. Rewriting the straight line equation in terms of linear regression equation becomes where y dash is the predicted value of y when x is given. Beta 1 is the slope, equivalent to m, and beta 0 is the intercept, equivalent to c, in the straight line equation. But how are slope and intercept calculated? Here is the formula to estimate beta 1, where x bar is the mean of x, y bar is the mean of y, xi is the actual data point of x, yi is the actual data point of y. This formula will give you estimated value of beta 1. After you get beta 1, you can easily calculate beta 0 by substituting beta 1 to this equation. You do not need to do manual calculation to estimate the parameters. Instead, your software that you use for modeling will automatically calculate and learn the parameters using the given dataset. Suppose beta 1 is calculated to be 19.73 and beta 0 is minus 14.45. Now you have the parameter value for the linear regression equation. Thus, putting these parameter values into our linear equation, our equation would look like. This creates the equation for our straight line that will be the best fit line, that describes the relationship between the two variables. The coefficient 19.73 means that for every 1 unit increase in x, y increase by 19.73 units. The intercept minus 14.45 indicates that the predicted value of y would be minus 14.45 when x equals 0. Now, we have the required parameters for the linear regression model. Now let's draw the best fit line on the scatter plot where data points have been plotted. Here we find that all the data points lie on a single perfect straight line. When that happens, the line can be drawn directly, even without calculating the slope and the intercept. However, in the real world, this is almost never the case. All the data points rarely align on a single straight line, because many factors may influence them. Now take this scatter plot, where all the data points do not lie on a single straight line. So, which line would be the best line here? Here, the goal of a data scientist becomes to decide on the straight line. That minimizes the distance between the actual data points and line itself. The straight line which can be drawn as close as possible through most of the data points will be acceptable. This is what is known as best fit line. Here the relationship between the variables is not perfect linear as the change in variable y is not constant. In the real world also, we don't see the perfect linear relationship. And all the points never follow a single straight path. Still, linear regression model can work here. The goal of linear regression analysis is to find the general pattern in the data. This is the case where you cannot draw a single straight line by hand. We must estimate slope and intercept. By applying our data points on regression model, suppose we got beta 1 equals 6.59 and beta 0 equals minus 56.12. Our best fit line equation would be. Thus, if this is the scatter plot and when we plot best fit line on this scattered plot, the distance between the point and the line itself is called the residual error or the noise. Let's imagine we plot many different lines through the data points. Let's take a line. We calculate the difference between each data point and the line. Take each difference as D1, D2, D3, D4, D5, D6, D7 and D8. Then square each difference, and then sum all of them together. This is called sum of the squared errors or sum of the squared difference or sum of the residual errors. Suppose we do it for each line. The line that gives the least value of sum will be our best fit line. The goal of the linear regression model is to estimate the parameters, beta 0 and beta 1, such that they define the straight line that minimizes the sum of the squared difference. To find the perfect line, linear regression do not rely on estimating many values of intercept and slope, but internally it uses OLS, ordinary least square, algorithm, to estimate these parameters such that sum of squared difference is minimized. The OLS method does this by finding the beta 0 and beta 1 that minimize this function. Y dash is the predicted value of y, for that x, by applying estimated parameters for the current line. The difference between the actual value y and the value predicted by the line is squared, and all the squared difference is then summed together. In the process of minimizing this function, OLS uses analytical methods to directly derive the formulas for the slope, beta 1, and the intercept, beta 0, that we saw earlier. Since the goal in linear regression is to minimize the sum of squared errors, the error term must also be included in the linear equation. After including the error term in the linear equation, our linear equation becomes. Here, the error term includes all the unknown factors that affect y. Y square. Squaring makes all errors positive. Positive and negative errors won't cancel out each other when summed. Secondly, squaring makes large errors appear larger than smaller error. 2 becomes 4, but 10 becomes 100. Then it tries to minimize that large error by shifting the line towards larger errors, even if that movement makes the line slightly away from the smaller errors or good points. The OLS algorithm will adjust the line's slope and intercept such that larger errors are reduced. Hope this explanation clarifies linear regression analysis in a simple way. So far, we have understood simple linear regression. This method can easily be generalized to multiple linear regression, where the influence of 2 or more independent variables on one dependent variable is analyzed.